The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let us start. So let me start by reminding you what we did in last lecture. So you take the black hole metric. So we explained that you can actually extend. So these are the black hole horizon. So you can actually extend the region outside the horizon to actually 4 total regions for the full black hole space-time. And then in this and this is a singularity. And of course, this is only the RT plane, and then you also have a S2. So now when you do analytic continuation, then in order to then we show that in order for the metric to be regular at the horizon, when you do this, when you go to Euclidean signature, then you want to identify tau to be periodic with this period. So in essence, you said when you go to Euclidean signature, then this RT plane become essentially a disk, and with tau is in the angular direction, and the rho, this R is in the radial direction. Okay, and the origin of this disk is the horizon. The origin of the disk is the horizon, and so when you say, so this tau have to be periodic. So that means if you put any series in this space-time, then that series must be at a finite temperature with inverse of this, which give you this h kappa divided by beta, and the kappa is the surface gravity. So you can do the similar thing with the Rindler, and the Rindler is just 1/4 of a Minkowski, which foliates it in this way. This is a constant rho surface. This is a constant eta surface. And again, when you do analytic integration in eta to Euclidean, and in order for the Euclidean analytic integration to be regular at the region, then the theta have to be periodic in 2 pi, and then the theta essentially become angular direction, and then this implies that the local observer in the Rindler space-time must observe a temperature given by this formula. Okay? Any questions regarding that? Good. So today, we will talk about the physical interpretation of this temperature. Okay. So let me just write down what this temperature means in words. So I will use black hole as an example. You can say exactly parallel things for the Rindler. He said if you consider a quantum field theory in the black hole space-time, okay, then the vacuum state, so when you put the quantum field theory, say, in the space-time, you always ask what is the vacuum. Then the vacuum state for this QFT obtained via the analytic continuation procedure where the analytic concentration procedure from Euclidean signature is a thermal equilibrium state. Let's go thermal equilibrium state with the stated temperature. Okay. Okay. So emphasize, when you want to talk about temperature, you first have to specify what is the time you use. Okay. So this temperature refers to this particular choice of time, and so this is the temperature corresponding to observer who are using this time. Okay. And this is the time, as we said, corresponding to observer living at infinity. And so this would be the temperature observed by the observer at infinity. So similarly, this temperature is the temperature for given of the radial observer at some location of rho. So this is for local observer. If you just talk about the eta, then the temperature is just h divided by 2 pi, because theta is periodic in 2 pi. And if you ask what is the temperature associated with eta, it's just h bar divided by 2 pi. Okay? So any question regarding this statement? So now let me, this statement itself is a little bit abstract, so let me elaborate a little bit. And let me make some remarks. So the first is that the choice of vacuum for QFT in the curved space-time is not unique. Okay, so this is the standard feature. This is a standard feature. So if you want to define a quantum field theory in the curved space-time, because in general in the curved space-time there's no preferred choice of time. So in order to quantize a theory, you have to choose a time. So depending on your choice of time, then you can quantize your theory in different way, and then you have different possibility, different possibilities of what is your vacuum. So in other words, in the curved space-time, in general, the vacuum is observer dependent. Okay. So of course, the black hole is a curved space-time. So the procedure we described, so the particular analytic continuation procedure we described, so the procedure we described corresponds to a particular choice. To a special choice. Of the vacuum. In the case of a black hole, this has been called to be the Hartle-Hawking vacuum. Because the Hartle-Hawking first defined it from this Euclidean procedure. And for the Rindler space-time, so we will see a little bit later in this class, in today's class, that this is actually the choice of vacuum is actually just corresponding to the standard Minkowski vacuum. Okay. reduced to the Rindler patch. Okay. So of course, you can actually choose the vacuum in some other way. For example, say if for black hole, instead of periodically identify tau with this period, we can choose not to identify tau at all. Okay, suppose for black hole in Euclidean signature, we take tau to be uncompact. Okay, so we don't identify. So this corresponding to a different Euclidean manifold. Okay, then that corresponding to a different Euclidean manifold. And through this, and again, you can really continue the Euclidean theory on this manifold back to Lorentzian to define a vacuum. Okay, and that gives you a different vacuum from the one which you identify tau. Okay, so this gives you a so-called Schwarzschild vacuum. Or sometimes people call it Bourwell vacuum because Bourwell have worked on it in the early days before other people. And in fact, this Schwarzschild vacuum is the most natural vacuum. This is the, in fact, this is the vacuum that one would get by doing canonical quantization in the black hole in terms of just this Schwarzschild time t, okay? So let me just emphasize. So this is a curved space-time. You can just put a quantum field theory in this space-time, and there's a time here, which is actually the space-time is time-dependent. So you have a time-independent Hamiltonian. So respect to this time. And so in principle, you can just do straightforward canonical quantization. And that quantization will give you a vacuum. And that vacuum would correspond to the same as you do analytic integration to the Euclidean and don't compactify tau. Okay, because there's nothing special. It's just like when you do the zero temperature field theory in the standard Minkowski space-time. But when you compactify tau, then you get a different vacuum. It's what we now call this a Howard-Hawking vacuum. And it's what you get the finite temperature. Okay? Is this clear? Yes.
How physical? So, in what sense are these different vacuums physical or not?
Yeah, I will answer this question a little bit. Yeah, just right now I want you to be clear. Right now we have two different vacua here, corresponding to two different ways of doing analytic integration.
Yeah.
And one way you compactify tau, and one way you don't compactify tau. And the way you don't compactify tau is actually the most straightforward way. So if you just do straightforward canonical quantization using that time, then that will be the vacuum you get. So that's why this is called Schwarzschild vacuum. Okay?
So do you then have a singularity at the horizon?
I will talk about that. So similarly, for the Windler, again, if you do straightforward canonical quantization in this space-time with eta as your time, then when you go to Euclidean signature, you won't compactify the Euclidean version of eta, then you won't compactify theta. Okay? So if you take the theta to be uncompact, then you get what is so-called Windler vacuum. So it just, again, can be obtained okay. So then you ask, then why do we bother to define those vacuum? Why do we bother to make this identification? Given that this is the most straightforward thing to do, say when we consider this quantum field theory in such curved spacetimes. So here is the key. And so that's where the geometric consideration become important. So again, let me just first use the black hole as an example case. So in the Schwarzschild vacuum, okay, so the corresponding Euclidean manifold is singular at the horizon. Okay, so we explained last time when you do this analytic continuation, the space-time is regular only for this periodic identification. Okay, for any other possibilities, then you will have a conical singularity at the horizon. So this implies. So this implies the Euclidean manifold is singular at horizon. Say if you compute the correlation functions, etc., then you can have singular behavior at the horizon. Okay. In particular, when you analytically continue to Lorentzian signature, then that means that observables, physical observables, often are singular. At the horizon. Okay, so when you need to continue to Lorentzian signature. For example, which actually I should have made it a p-set problem, but I forgot earlier. For example, you can check yourself that just take a free scalar field theory. You compute the stress tensor from this free scalar field theory, and you find the stress tensor of this theory blows up at the horizon in the Minkowski vacuum. Okay? And this is not the case for the vacuum we obtained by doing analytic computation this way. Okay? So this is not the case for Hartle-Hawking vacuum. Okay? So Hartle-Hawking vacuum just is the name for the vacuum we obtained by this analytic continuation procedure, for which all observables are regular, just by essentially by definition, by construction. Okay. So essentially by construction, because Euclidean manifold is completely smooth, and if you want to compute any correlation function, for example, you can compute the Euclidean signature, and then analytically continue back to the Lorentzian signature. Because it's smooth at the horizon in the Euclidean signature, analytic continuation back will also give you a regular function at the horizon there. Okay? So similar remarks apply to the Rindler space, and the standard, this Rindler vacuum will be singular at this Rindler horizon. Okay, will be singular at Rindler horizon. So, since from the general relativity, the horizon is a smooth place. Okay, the curvature there, there's nothing. The curvature there can be very small if you have a big black hole, etc. So, so physically, we believe that this Hartle-Hawking vacuum are more physical than, for example, the Schwarzschild vacuum. Okay, but Schwarzschild vacuum is still often useful for certain purposes. But if you want to consider, say, physical observables, then the Hartle-Hawking vacuum should be the right one to use, if you don't want to encounter singularities at the horizon. Any questions? Yes?
Is there a temperature associated with the Schwarzschild vacuum?
No. Yeah.
T equals 0?
Yeah. Yeah. Yeah, because for example, Euclidean tau is uncompact. Yeah.
So singularity of the physical variables goes up is a unique way we consider the Hartle-Hawking.
Yeah, that's right. Yeah.
No other reasons?
I would say this is the physical reason. If I think about it, I might find other not so essential reasons. Yeah, but at the moment, I could not think of any others. Yeah.
So if I understand correctly, so when you quantize a theory in curved spacetime, you have to choose a space-like foliation of your spacetime, and then you quantize it on that foliation, basically.
Yeah.
So the problem is that, I still don't understand, so the different ground states that you get for different possible quantizations based on different foliations, like, they're not, to what degree are they compatible versus incompatible with each other? Like, I mean, are they like at odds with each other, or are they just, like, is one more real than another one, or is it just sort of an artifact of your coordinates, and there are things that we can do which are independent of which one we end up with?
Yeah, so in general, first, in general, they are physically inequivalent to each other. For example, in this case, the Schwarzschild vacuum is physically inequivalent to the Hartle-Hawking vacuum. And actually, with a little bit of work, one can write down the explicit relation between them. And so from the perspective of the Schwarzschild vacuum, the Hartle-Hawking vacuum is a highly excited state, and vice versa. So vice versa. And so yeah, so for local observable, say in the for local, it depends. I think the vacuum is more like yeah, you have to, sometimes certain vacuum is more convenient for certain observer, and certain vacuum is more convenient for that observer. Sometimes depend on your physical applications, etc. Yeah. Any other questions?
So we cannot treat these two vacuums as like some transformation.
Yeah, there is some transformation between them.
So can we say it's just the same, like we do canonical transform to an operator or something?
No, they're different states. They're completely different states. You can relate them in a certain way, but they're different states. Yeah, they're different states.
If they are different, then why we cannot say one is wrong? They are because, for example, if it's singular, it's not physical, why we just don't discard?
Sorry?
Why?
Yeah. Physically, we do discard it. Physically, we don't think the Schwarzschild vacuum is. So here, there's assumption. So assumption is that we believe that physics is non-singular at the horizon. So this is a basic assumption. And if that's the basic assumption, then you should abandon Schwarzschild vacuum as the physical choice of the vacuum. You should just, then you say, then if you really do experiment in the black hole geometry, then what you will discover is the property of the Hart-Hawking vacuum. But if our physical assumption is wrong, that actually black hole horizon is singular, then maybe Schwarzschild horizon will turn out to be right. But in this case, but we actually don't know, we cannot really do experiment in the black hole, so we cannot really check it. Right.
But we can measure black hole temperature from infinitely far away, and in the Schwarzschild vacuum, it will be 0.
No, but you cannot measure it. We have not been able to measure it.
Okay. And what about the LHC, like micro black hole production? Like if
Yeah, first produce the black hole first. Yeah, we will worry about after we have produced the black hole.
If they didn't radiate, they would not decay at all, right?
Yeah, then you may also not see it. Yeah. Anyway, so okay, so this can be considered as a physical interpretation of the temperature. Is that the regularity at the horizon forces us to be in this Hart-Hawking vacuum, and then the Hart-Hawking vacuum is like a thermostat. Okay, so now let me explain why this thing, they will behave like thermostats. Okay, so let me go to the second thing I will explain today. Is the physical origin of the temperature. Okay. So again, I can use either black hole or the Rindler example. The mathematics are almost identical, but I will use the Rindler example because the mathematics is slightly simpler. Okay. So I will use the Rindler spacetime. So I will explain. So I will explain using the. So I will use the Rindler example. So I will explain A, that this choice of theta to periodically identify theta plus 2 pi corresponding to the choice of a Minkowski vacuum. Okay. Then the second thing I will do is I will derive this temperature. Derive the temperature. Using a different method. Okay, so that's what I will do today. So here, when we say this temperature, we just directly read the temperature from the period of the tau. Okay. But today I will really derive the thermal density matrix, and then you will see that this temperature is indeed the temperature which appear in the density matrix. Any questions? So these two together also amounts to the following statement. So this is an important statement, so let me just write it down. So this A and B also amounts to be the following, also is equivalent to the following statement. Is that the vacuum is that the Minkowski Minkowski vacuum. The standard Minkowski vacuum, when you do your quantum field theory, the Minkowski vacuum appears to be a thermal state with temperature h bar divided by 2 pi, or T equal to h bar divided by 2 pi in terms of eta. Okay, depending on which time you use, to a Rindler observer of constant acceleration A. Okay? So A said actually this choice, we take theta goes to a periodic 2 pi, actually we are choosing the Minkowski vacuum. So, and then the second statement is that but the standard Minkowski vacuum, which appears to be 0 temperature to an ordinary Minkowski observer, then appears to be a thermal state to a Rindler observer. Okay, so that's the physical content of this thing which we will show. Any questions on this? Yes?
So I have a small question, right? Is the Hartley-Locking vacuum and the Schwarzschild vacuum, do they belong to the same Hilbert space? Or?
It's actually a tricky question. In some sense, they don't really belong to the same Hilbert space. Yeah, just when you talk about quantum field theory, it's a little bit tricky when you have infinite number of degrees of freedom. Yeah. Yeah, but one can write down the relation between them. Yeah, one can write down a relation between them, and then if you take the modulus of that vacuum, then you find it's actually infinite because of because you have infinite number of degrees of freedom. Yeah. Yeah, you can. It's not possible to normalize that state. Okay, so that's what we are going to show. Hopefully, we will reach it by the end of this hour. But before do that, we need a little bit preparation to remind you of a few things. Okay, to remind you of a few things. So once we go through these preparations, and then the final derivation only takes less than 10 minutes. So first, is that there are actually two descriptions of a thermal state. Description. So let me remind you, there are two descriptions of a thermal state. Okay. So I will use harmonic oscillator as an example. Okay, so now let's consider harmonic oscillator at finite temperature, a single harmonic oscillator at finite temperature. Okay? So the standard way of doing it is that if you want to compute the expectation value of some operator, of some observable at finite temperature, you just do the standard canonical average. Okay? So the H would be, say, the Hamiltonian of the single harmonic oscillator. And the Z is the partition function. So this can also be written as trace X and the thermal density matrix. So the thermal density matrix is 1 over Z by minus beta H. Okay, and the Z is just the sum of all possible states. Okay? So this is the standard way you would do, say, the finite temperature physics. So this, of course, applies to any quantum systems, also quantum field theories, etc. But actually, there's alternative way to do thermal physics. So this was realized by Umezawa in 1960s. So he said, instead of considering the thermal density matrix, let me just consider two copies of the same. Let's consider two copies of harmonic oscillator. Okay, let's just consider, let's double the copy. And then now we have H1. Then the full Hilbert space for these two copies will be the H1 of one system, tensor product of H2, and the Hilbert space of the other. And then you will have H1, H2, the Hamiltonian H1, H2 associated with each of them. Okay, but of course these two H are the same. Okay. Then in such a system, then a typical state, would be, say, of the form sum Mn, Amn, M1 tensored with N in Q. Okay? So the general state, say, of this doubled system will be like this. Okay, so this is two copies of same system with no interaction with each other. So now he say, in order to consider thermal physics, let's consider special states defined by the following: 1 over square root of z sum over n Okay, so now he said, now let's consider the following states. Okay, so this is an entangled state between the two systems because so this is an entangled state. So the key observation is that if you want to consider the thermal physics, is that for any observable, say this x, so let me call it 1, say which is in one, which only acts in one of the system. Say, for example, only act on the first system. Okay, so let's consider any such observable. So now, if you take the excitation value between this psi, so if you take the expectation value between the psi, the x between the psi, okay. So so you essentially have psi squared, then you have z 1 over z. Then this also double become beta En, and then this just become 1 over z sum over n between minus beta En and x n. So this is the thermal average. Okay. This is thermal average. So do you understand why? You can also consider, because if we are interested only in system 1, then you can just integrate out system 2. You can trace out system 2. Say, suppose you trace out the system 2 of this state. Then, of course, what do you find? Which is the density, which is the thermal density matrix of the system 1. Okay? So in other words, the thermal density matrix in one system can be considered as an entangled pure state of a doubled system. And because we know nothing about the other system, once you trace the other, once you trace out the other system, then you get a density matrix. And this density matrix comes from our insufficient knowledge of the other system. Okay? So this is another way to think about this thermal behavior. Do you have any questions on this? So the temperature arises due to our ignorance of system 2. Okay? So of course, if you have full knowledge of 1 and 2, then this would be just the psi is just a pure state. It's just just a very special pure state. But if you don't know anything about system 2, and if you're concerned only about system 1, then when you trace out system 2, then you get the thermal density matrix for 1. So let me make some additional remarks on this. So make some further remarks. First, this of course applies to any, even though I'm saying I'm using the harmonic oscillator, this of course applies to any quantum systems, including the QFTs. Okay? So the second remark is that this psi is actually a very special state. This psi is invariant under H1 minus H2. H1 minus H2. So you can see it very clearly from here. Is that if you act H1 and H2 on this state, H1 minus H2, because both n have the same energy, so they just cancel. Okay? So this is invariant under this it's invariant. I should say, more precisely, it's invariant. It's annihilated by H1 minus H2. And it's invariant under any translation created by H1 minus H2. Okay?
So here you assume that the spectrum in H1 should be the same as H2.
Yeah, I just doubled the system. It's two copies of same system. So the third remark, so this now relies on the harmonic oscillator. For the harmonic oscillator, we can write this psi in the following form. So this you can check yourself and only write down the answer. You can easily convince yourself this is true. Some of you might be able to see it immediately just on the blackboard. Okay, so you can actually write this in the, so you can write this as some exponential of some, so A1 and A2 are creation operators respectively for two systems. And then the 0, 1 and 0, 2 are the vacuum of the two harmonic oscillator systems. And you can easily see yourself when you expand this exponential, then you essentially just take the power of n, and then that will give you n on, yeah, when you act on 0, 0, then that will give n times n, okay? So to write, so this is normally called a squeezed state. So this tells you that this vacuum, this psi is related to the vacuum of this system by some kind of squeezed, so this is a squeezed state in terms of the vacuum. So this form is useful for the following reason, is that now based on this 3, one can show it's possible to construct two oscillators, which are called B1 and B2, which annihilate the psi. Okay? So B1 and B2 are constructed by the following. So again, this you should check yourself. It's easy to do. A little bit algebra. So this theta, so Koch theta, is equal to 1 over 1 minus exponential minus beta omega. So the omega is the frequency for this harmonic oscillator system, and the sinh theta is equal to okay. So this B1 and B2 are related to A1, A2 by some linear transformation. So what this shows is that, well, 0, 1 and 0, 2 is vacuum for A1 and A2. And this psi is vacuum for B1 and B2. So that may be considered just corresponding to different choice of vacuum. Okay? So as we will see later, the relation between so-called Hazel-Hawking vacuum and the Schwarzschild vacuum is precisely like this. Okay? They just corresponding to different choice of oscillators. And in particular, their relation is precisely of this form. Yeah, because, say, if you consider some free series, because the free series essentially just reduced to harmonic oscillators. Okay, so this is the first preparation. And those things are very easy to check yourself because this is just a single harmonic oscillator. Any questions on this? Oh, by the way, this is called a this kind of transformation is often called Bogoliubov transformation. So the non-triviality, so the non-trivial thing about this transformation is that in the expression for B1, B2, a dagger appears here. Okay? If there's only A appear here, then B1, B1, B2, A1, A2, they will have the same vacuum. Okay? Because they will annihilate the same state. So the non-trivial thing is because of the dagger appearing here. So now, now the state which they annihilate are completely different and related by this kind of squeezed state relation. Okay? Yes?
So it's related to the H1 minus H2?
Sorry?
The operators like B1, B2 are somehow similar to the H1 minus H2?
Not really. No, the H1, H2 is, you can write down H1, H2 in terms of B1 and B2. You can certainly do that. Yeah, but H1, H2 is also very simple. You write in terms of A1 and A2.
For that transformation, it seems if we just dagger B1, we get, never mind.
Yeah, you can find the B1 dagger. Yeah, just take the conjugate. Good, so this is the first preparation, which is just something about the harmonic oscillator, which actually can be generalized also to general quantum systems. So the second is I need to remind you a little bit the Schrödinger representation of QFTs. Okay? So normally when we talk about quantum field theory, we always use Heisenberg picture. We don't talk about wave function. But there's an equivalent formulation of course quantum field theory, which you can just talk about wave functional, and talk about in terms of the Schrödinger picture. So for example, let me just consider a scalar field theory. A scalar field theory. Okay. Then the Hilbert space, then the configuration space of this theory of this system is just phi x. Okay, evaluated at some given time. Okay, only with say evaluate at t equal to 0, for example. So let me just write it as phi x. Okay. So the configuration space is just all possible values phi defined in the spatial slice. Okay, so this is your configuration space for the quantum field theory. And the Hilbert space of the system just given by all possible wave functionals of this configuration space variables. Okay. Okay. So if you feel this is a little bit too abstract to you, then just think of the space is discrete, and then there's only and then you can just write this as some discrete set of variables. Okay, then become identical to the ordinary quantum system. So one thing to remind you, so two things to remind you, two more things. First, just as in quantum mechanics, if you ask the value of, say, at time t2, you are in the eigenstate of this phi with eigenvalue phi 2 and overlap with that T1 in the eigenstate of phi with eigenvalue phi 1. This is given by a path integral d phi. This is given by a path integral. You integrate with the following boundary condition. Okay? And S is just the axiom for this theory. In particular, by taking a limit of this formula, one can write down a path integral representation of the vacuum, or of the vacuum function, a vacuum wave function. So the vacuum wave function. So in this case, will be very functional, can be obtained. So if you have a vacuum state, then you just consider the overlap with the vacuum to your configuration space variable. So I will denote it by psi 0, phi x. So this is the vacuum. And this has a path integral representation. Is that you complexify your time. Okay, so suppose this is your real time, and this is your imaginary time, which I call TE. Okay, you complexify your time, and then you integrate the path integral over all negative imaginary time. Okay, so this can be written in terms of path integral S d phi TE x. So you go to Euclidean, but with all the TE, but integrate over all TE smaller than 0, with the boundary condition TE equal to 0 x equal to phi x, and your Euclidean action. Okay, I hope you are familiar with this. This way of obtaining the vacuum Green function. So you mind, if this is not familiar, you remind yourself, how do you get the wave function of a harmonic oscillator in the vacuum from path integral? Yes?
Can you give an overall first view picture? Why do we need this Schrodinger representation of QFT? Why highly limited network?
You will see it in a few minutes, because I'm going to use those formulas. Yeah. Yes?
So one question is that what is the analog of the wave equation for the wave functional? Like, what is the Schrodinger equation for the wave functional?
The same thing. I partial t psi equal to h psi.
Okay.
Yeah, you just have more degrees freedom. The quantum mechanics works the same.
Okay.
Yeah. So is this familiar to you? If not familiar to you, I urge you to think about the case of a harmonic oscillator. For the harmonic oscillator, that will be the way you obtain the ground state wave function from the path integral. Is that you first analytically continue the system to the Euclidean, and then integrate the path integral all the way from minus Euclidean time equal to infinity to Euclidean time equal to 0. Let me just write down the. So the standard quantum mechanics, if you want to write down the ground state wave function, so that's what you do. Again, you go to the path integral, you go to Euclidean. And you integrate over all TE smaller than 0. Then with the boundary condition that x evaluated at TE equal to 0 equal to x, so that gives you the wave function. Okay? Give you the wave function. Okay, now with this preparation, that's just in ordinary quantum mechanics. And this is a generalization of that to quantum field theory. You just replace that x by phi. Okay? Good. So now let's go back to prove the statement we claim we are going to prove, this one. Okay? So now let's come back. So we finish our preparation. Now come back to Rindler space. Rindler. Say, let's consider scalar field theory, for example. So let me just remind you again, this Rindler, so write down some key formulas here. So Rindler is the right quadrant of the Minkowski time, which separated by this night cone. Suppose this is x, this is t, then Minkowski span is minus the t square plus the x square, and the Rindler patch is minus rho square, the eta square plus the rho square. Okay, and so this is the rho equal to constant, and this is the eta equal to constant. And here is eta equal to minus infinity. So here is eta equal to plus infinity. Okay, so space-time foliate like this. Okay, and when we go to Euclidean signature, for the Minkowski, of course, we just t goes to minus ITE. I call this Euclidean time. For the Rindler, I will do minus I theta. Okay, use my notation before. So in the Euclidean signature, the Minkowski, standard Minkowski just become TE squared plus TX squared. And this Rindler is just rho square, the theta square plus the rho square. In particular, with theta identified to be with period 2 pi, the Euclidean analytic calculation of Minkowski and Rindler are actually identical. Both of them are the full Euclidean, two-dimensional Euclidean space. Okay? So if you do the standard Minkowski, you just replace x by TE. But for the Rindler, you just replace it by rho theta. Okay, by rho theta. So they just correspond to different foliation, this corresponding to the polar coordinate, this corresponding to the Cartesian coordinate. So the remarkable thing is that even in the Lorentzian signature, the Rindler is only part of the Minkowski space-time. Okay, but once you go to Euclidean, if you do this identification of theta equals theta plus 2 pi, they have exact the same Euclidean manifold. Okay, just identical. So this immediately means one thing. So this immediately means one thing is that all the Euclidean observables just with a trivial coordinate transformation from this to the from the Cartesian to the polar coordinates, all the Euclidean observables are identical. In two series. Okay.
What is that down there? Are identical. What is R sub e squared?
Yeah, just this means the Euclidean two-dimensional space-time. R2.
Oh, I see.
Yeah, let me just write it. This is R subscript E squared 2. So this is just a two-dimensional Euclidean
Yes, got it. Yes.
space. Yeah. Okay. So from here, we can immediately read the conclusion we said earlier. Because for Minkowski, so if you compute the Euclidean correlation functions and then you analyze it back to the Lorentzian signature, what you get is you get the correlation function in the Minkowski vacuum, in the standard Minkowski vacuum. Okay. So for Minkowski and back to Lorentzian. So the typical observables, so the Euclidean say functions, correlation functions, just goes to correlation functions in the standard Minkowski vacuum. Okay. Yeah, this is just trivial QFT in your high school. But with this top statement, we reach a very non-trivial conclusion. Is that for Rindler, when you go back to the Lorentzian signature, then that tells you for the Rindler, when you do that analytic integration and back to the Lorentzian signature, what you get is that you get a correlation function in the Minkowski vacuum, in the standard Minkowski vacuum, but for observables restricted to Rindler. Okay. Okay, because it's the same thing. When it's the same function. When you do analytic integration, just you do it differently. It just analytic integration procedure is a little bit different. And when you do go to Rindler, you just get observable restrict to the Rindler patch. Okay, so the Euclidean thing are exactly the same. Okay, so that tells you that the corresponding Lorentzian Rindler correlation function is the same as the correlation function in the standard Minkowski vacuum, but you just restrict to the Rindler patch. Okay. Okay, now is our final step. So now let's talk a little bit more about the structure of the Hilbert space. So now I have to derive the temperature. But somehow in the Minkowski, there's no temperature. Here, there's no temperature, is T equal to 0 from your high school. And here, we must see a temperature. So where does this temperature come from? So now let's look at a little bit, look at the structure of the Hilbert space. Okay? So using that picture, so let me write here. So the Hilbert space of the Rindler, so this is all now in the Lorentzian picture. So the Hilbert space in the Rindler is essentially the wave function, all possible, say, square integrable wave functional of the phi, which defined in the right patch. Okay, so when we define this wave functional, we evaluate phi at a single time slice. So let's evaluate the slice which eta equal to 0, which is just here. Okay, so which phi r is essentially just phi for x greater than 0 and the t equal to 0. Okay. Okay, just the right patch of the right half of the real axis. So this is the structure. So this is the Hilbert space of the Rindler. And of course, you can also write down the Hamiltonian for the Rindler with respect to the eta. Okay. So this is called Rindler Hamiltonian. And as I said before, you can quantize this theory using this Hamiltonian. Then you will get, so you can quantize this Hamiltonian, you can construct all the excited states. So let me just label them by n. Say label by n, say this completed set of energy eigenstates, for HR, say with eigenvalue, say En. Okay, you can just quantize it, then you can find your full state. In particular, the ground state, when you do that, is what we call the Rindler vacuum. Okay, we said before that if you just do straightforward canonical condensation, you get the Rindler vacuum. Okay, which is different from the vacuum which we identify theta by 2 pi. At this, we just straightforward quantize with respect to eta. So now let's go back. So this is a structure of the Hilbert space in some sense for this Rindler. For this Rindler. So now let's look at the Minkowski, the Hilbert space for the Minkowski. So Minkowski is defined, by Minkowski I mean a series defined for the whole Minkowski space-time is this T, okay, quantized with respect to this T. So this would be just standard psi phi x. Okay, now this x can be anything. Okay, and then we also have a Minkowski Hamiltonian defined with respect to T, to capital T. Okay, so this is the standard Minkowski Hamiltonian. And the vacuum, which I denote to be the Minkowski vacuum, is M. Okay, and then the vacuum functional phi x is just phi x 0 m. Okay. Okay. So now the key observation is that. So the key observation here. So now the key observation is that phi x, which this phi x is for the full real axis, full horizontal axis. So this is in some contain phi Lx and phi Rx. It's corresponding to the value of phi evaluated to the right, or the right patch, and the value evaluated to the left patch. Okay? So the space of phi x, so it's the combination of space of phi Lx for the left part and space for the phi right part. Okay? In particular, this tells us the Minkowski-Hilbert space, which is defined as a functional of this full phi x, should be the tensor product of the Rindler to the right, tensor product of the Rindler to the left. Notice that we talk about this right Rindler, but there's a similar Rindler to the left. Okay, so but the structure of the Minkowski space, Hilbert space, is a tensor product of the two. In particular, this ground state wave functional, you can write it as phi Lx and phi Rx. Okay. So this ground state wave functional should also be understood as the functional for phi L. Okay, so now here is last key. So here is last key. So remember the wave function, the ground state wave function obtained by doing path integral on the Euclidean half plane. So T is smaller than 0. Okay. So so let me just draw the Euclidean space again. X T E. So the Euclidean, so the wave function can be written as d phi Tx Tex minus SE, the Euclidean action, on the lower half plane of the Euclidean space with the boundary condition okay, remember this is the from path integral, that's how you obtain the so that means you integrate over all this region, path integral over this region, then with boundary condition fixed at here. Okay, we do this path integral, you get the wave function, the Minkowski wave function, Minkowski vacuum wave function. Okay? Now, here is the key. So this half space, when I write in this form, you treat this T as the time. Okay? But now let's consider different foliation. I don't have colored chalk here. I can consider different foliation. Is that foliation in terms of the theta? Then you just have this foliation. So for each value of theta, you have a rho. Then this is so integration from minus theta to theta. Okay? So if you think about from this foliation, so think about from this foliation, then this path integral can be written as the following. D phi theta rho, which you fix phi theta equal to minus pi rho here, when theta equal to minus pi become x equal to phi Lx. And the phi theta equal to pi theta equal to 0, rho equal to phi r x and exponential minus s e. Okay? So these two should be the same. I just choose the different foliation to do my path integral. Okay? But now if you think from this point of view, this is precisely like that. Precisely like that, because theta 0 and theta minus pi are just two different times in terms of this Euclidean Rindler time. Okay? So this you can write it as phi. Yeah, so let me write one more step. So this can be written as phi 2 exponential minus IH T2 minus T1 phi 1. Okay? Okay? So this last step can be now written as so this last step I can think in terms of the time using the Rindler time. This can be written as psi r exponential minus I minus I pi, because we have a Euclidean time h Rindler Hamiltonian phi L. Okay? So this tells me that Minkowski wave functional can be written as the following. Can be written as phi r exponential pi hr phi L. Okay? So now let me expand this in the complete set of states. Of HR, then this is sum over n. So if I expand in terms of complete set of energy eigenstate of HR, then this is, say, this wave function so with this chi n equal to chi m phi equal to phi. So remember, this n is defined from this Rindler Hamiltonian. Okay. So now let me erase this. So I can slightly rewrite this because I don't like this complex conjugate. I can slightly rewrite this. It's psi 0 phi x is equal to sum over n exponential minus pi e n chi n phi r and chi n tilde phi l. So chi n tilde are defined to be phi n star phi l. So this chi n tilde can be considered just like in ordinary in quantum mechanics. This can be considered to belong to a slightly different Rindler space, a Hilbert space whose time direction is opposite. So when you switch the direction of time, you put a complex conjugate. So this complex conjugate can also be think of just as a wave function in the Hilbert space with the opposite time direction, okay? Which is opposite to the Rindler we started with, to the right Rindler, to the right patch Rindler. Okay? So now this form is exactly the form we have seen before in this Umezawa way to think about thermal state. So this is exactly that, because so this tells you that the zero in the Minkowski vacuum is the sum over expansion minus pi En with n Rindler of one patch tensor n Rindler of the other one. So this is the other Rindler should be considered Rindler of the left, except we should quantize the theory with the opposite time direction. Okay, with the opposite time direction, which give you this Rindler tilde Rindler left. So this is just precisely the structure we saw before. In particular, if you are ignorant about the left Rindler, you can just trace it out. Trace out the left. Trace out the left part of this ground state wave function. Then, of course, then you just get rho Rindler, the thermal density matrix in the Rindler, and this is equal to, of course, 1 over Rindler expansion minus 2 pi h r. Okay? And we see that the beta is equal to 2 pi. But this is the beta associated with eta. Okay, this is the beta associated with eta. As we said, when you change to different observer at different rho, then you have to go to the local proper time. But this is precisely what we found before. Okay? So now we understand that the thermal nature of this the thermal nature of this Rindler observer is just precisely that, because this observer cannot access the physics to the left patch, but the vacuum state of the Minkowski space-time is an entangled state between left and the right. And when you trace out the left part, then you get the thermal state on the right part. Okay? So that's how the temperature rises. And that's how the temperature rises. And the same thing can be said about black hole, which we will say a little bit more next lecture. Yeah, let's stop here.